My name is Farhadi from Ericsson, and together with Claude, I will give an overview of Hexa-X-II WorkPackage 4 and WorkPackage 5 enablers on radio and devices for 6G. I will first give an overview of value-based holistic radio design that we have considered in this project. I will give a very brief overview of radio design components that we considered in this design methodology, and will give a short overview of radio design requirements that we specified in this project. And then we will go through different device classes that we would have for 6G, and also the radio scenarios that we specified for evaluations and the design purpose. And then we will continue with an overview of the enablers on the radio side and also on the device side. In this project, we considered works towards holistic radio design, which considered the entire radio system and the interdependencies that exist between different elements, including radio device capabilities, such as radio hardware, and also signal processing capabilities that we would have in devices. We also considered deployment scenarios and different frequency bands, and also the use case specifications, including the aspects related to the mobility, type of environments, and service requirements. In this design methodology, basically, we considered both KPIs and also KVIs, where KVIs stands for key value indicators, as part of the design process. Here we try to perform optimizations of the overall radio systems to improve the KVIs while we would fulfill the requirements in terms of KPIs. This optimization is carried out in different levels, including the deployment and the considerations for the deployment, like the different frequency range that are considered. And also we consider the RF front end and optimizations of different transmission schemes by taking into account the radio device features and RF hardware impairments that would impact the system performance. In this design methodology, we considered both software aspects and try to optimize the software aspects together with the hardware domain aspects, with the aim to provide a low-cost solution, basically. So that was the main focus, or I would say one of the main focus. To facilitate this holistic radio design, in Hexa-X-II projects, we defined specific radio scenarios based on selected use cases. So basically, in the project, we considered a wide range of 6G use cases, which has been identified in the project, and they are grouped into use case families. And next, for each user family, we have specified service requirements in other work packages in the project. And we try to map the service requirements to the corresponding radio requirements, such as data rate, latency, localization resolutions, and accuracy, and so on. Based on this defined set of requirements, we defined a set of representative radio scenarios. That these scenarios could be used for design and also evaluation purpose. So these design scenarios or these representative radio scenarios are specified for extreme requirements, such as extreme coverage, extreme data rate, and extreme connection density, and extreme low latency and high reliability. So these are the 4 radio scenarios that we considered that are specified based on stretch requirements that we would have in 6G scenarios. And then for each of these scenarios, we try to design the systems with the aim of improving the KVI requirements, in terms of sustainability aspects and also trustworthy and inclusiveness. Following this methodology, for each radio scenario, we associated representative use cases and specified the radio requirements in terms of different KPIs, such as data rate, reliability, and latency, and so on, both for communication purpose and also for localization and sensing purpose. So basically, these type of requirements would be used during the design process and also evaluations that we are going to have in the project. So here you can see one sample table that we have that summarize these type of requirements or radio requirements that we would have for each of these scenarios. And in each of the scenarios, one or few of these KPIs would have relatively higher requirements, like the one that marked by green in this table. So in the next, Claude will continue with sharing some insights from the projects on the future devices that we would have in 6G.
Thank you, Hamid. Good afternoon. So I will start in it with a short definition. So when we zoom on the design of devices, what are we actually considering? So what we mean is an end device being connected via radio link to the network and either generating or consuming data, so transmitting or receiving data wirelessly. Those are the devices we consider, and there could be many different types of devices. Those could be phones, those could be small sensors, those could be computers, headsets, whatever. So the list is rather broad. And if you have a look at the picture at the bottom, so there are mainly three aspects on which we focus. So the first one on the left is the hardware and RF transceivers, which are obviously needed for the radio communication, and those could be in many different bands. So those are seen in a broad way. Then in the center, we have the more digital system on chip integration with dedicated hardware for connectivity, with a general purpose hardware for system and design device management. So multiple functionalities embedded there. And on the right, you have, for the specific category of low energy devices, dedicated hardware components and protocols as well to manage the zero energy devices. So this is at high level the focus that we have in the WorkPackage 5 device design. Okay, so how do we get from use cases to various device classes such that we can solve those different device families? So we start from the use cases, and as it was mentioned by Hamid already, we start from the 6 main use case families that were developed within Hexa-X and Hexa-X-II projects. And for each of those 6 families, there are a number of different use cases being proposed, and a few have been selected. So the ones which are highlighted in the boxes, and those have been refined such that they can be connected to specific device classes. So we have initially defined 4 main categories of device classes. So the energy neutral, the reliable high data rate with bounded latency, the high reliability, low latency, and then the enhancements on the machine time communication devices. So those were the 4 main classes that were described in more detail, especially in the Deliverable 5.2. And then 2 additional classes that will be considered in the future. So the enhancements on the MBB or URLLC that could come up later in the project. So you can see on the chart, one way to position those different device classes. So there are lots of dimensions, of course, to consider those devices, but 2 dimensions are illustrated on this chart. On the horizontal axis, you have the requirements in reliability, latency. So the more you go to the right, the stricter those requirements get. And on the vertical axis, you have the data rate expected for those different device classes. So for example, if you consider the energy neutral class, this is the one closest to the origin of the axis, because obviously for energy neutral devices, you don't have so much power, so you will not achieve gigantic data rates or very strict requirements on the reliability latency dimensions. But of course, you focus much more on the minimization of the power consumption of the device. On the other part of the chart, then you have all the families which range from limited requirements on reliability, latency, but high data rate on the left, or to the bottom where you have somewhat more reduced requirements on data rate, but much stricter requirements on reliability and latency. So those are how we position the different device classes in this work package.
Thank you, Claude. Based on these different devices that are defined and also the radio requirements that I mentioned earlier. So for each of these scenarios, we specified the relevant deployment options, mobility options, relevant frequency bands, and the specific category of devices that would be associated to the radio requirements. So here you can see different examples that for each of these radio scenarios. For example, for eHealth for all, we can see how integrated NT and NTN would provide extended coverage so that with the relevant device family, we would be able to support such kind of use cases. In the project, we considered different aspects toward holistic radio design, including the architecture and deployment, that addressing the hardware architectures for integration of JCAS, for example, and the services that would be, in addition to communications, would be provided by 6G radio. And also aspects related to the deployment, for example, distributed MIMO and also RIS as components that would facilitate coverage extensions with relatively lower cost. We also considered radio link modeling that would cover channel modeling in different frequency bands and also link level signal modeling for design and evaluation purpose. And also we studied different signal processing and algorithms that would operate in baseband, such as the waveforms that would be used, modulation, coding, and resource allocation. And also we have worked on extensive AI-enabled air interface solutions that could operate either at a transmitter or receiver to improve the performance at relatively low cost. And also we look at flexible spectrum access solutions for sharing spectrum and also the coexistence of 6G with 5G and with other radio services. And also we look at the low latency random access solutions. And overall, we also had a focus on KVI aspects that covering the sustainability aspects, in particular reducing the energy consumptions, and also the trustworthy radio solutions so that we can leverage on features like JCAS to enhance the security and privacy of the 6G radio. So the key radio design enablers can be considered in different categories. So we have had studies related to channel modeling, waveform and modulation design, and massive MIMO solutions for higher frequencies, in particular Sub-Terahertz. And also we have had link level simulators for this. Also, we have investigated extensively intelligent radio air interface design with the focus on FR1 and FR2, which we would expect to have a high importance still in 6G timeframe. So here we investigated different AI solutions, for example, for hardware impairment compensations, radio resource allocations, channel prediction, channel compression, beamformings, and also coding design, and several other use cases for AI in the physical layer. Also, we have investigated different modulations, waveform, and coding solutions. We, in particular, look at the different solutions for distributed MIMO transmission, different type of beamformings, either coherent beamformings, non-coherent beamformings, and several solutions in that domain. Also, we have investigated RIS-assisted transmission and investigated RIS as a new component into this overall radio design paradigm. We also investigated different solutions towards enabling joint communication and sensing, where we have looked at the sensing architecture, waveform optimizations for joint communication and sensing, also resource allocations and protocols for integration of JCAS into this communication system. And also we look at the security and the resilience aspects and also the physical layer privacy aspects of JCAS, basically. And another area that we investigated in the project was spectrum sharing and coexistence, where we investigated different solutions for multi-rat spectrum sharing and also solutions for low latency random access. And as I already mentioned, we had focused towards sustainability aspects to investigate where and how we could have sustainable radio solutions, in particular on lowering the energy consumptions, and also trying to have inclusive radio by lowering the overall cost on the radio side by leveraging the new technologies and new design methodologies such as AI, for example. And also we investigated trustworthy aspects of the radio design. This is just illustrations of what I mentioned, so I just leave it to Claude for an overview of the enablers on the device side.
Okay, maybe you can quickly click 4 times then to illustrate how we tackle the design of the device. So the first task is classification of the device classes that I mentioned and detailed already. And then we have 3 more technical tasks on the design and hardware and RF transceivers for 6G, on the trustworthy system on chips, and on the ultra-low power design. And I will illustrate the ones from the task number 2 in the next 2 slides. So for Sub-Terahertz design, this is a very new frequency band, so there are lots of specific challenges. And the first one that we tackle on the upper left is to dimension those systems, because they believe to require many more antennas due to the specific propagation and wavelength that we have. And this leads to many different architecture template choices. So we are minimizing the energy consumption or the power consumption by comparing different architectures and selecting the most promising one in hybrid MIMO frameworks. This is one first aspect on energy efficiency. A second aspect is non-idealities coming from the front-end hardware. So this is modeled, for example, of the bottom left by looking at phase noise models for specific architectures, considering the way the local oscillator is distributed to the different antennas and the impact it has on limiting the system performance. And also on the upper right, this is generalized to modeling many different types of hardware idealities, not only the phase noise, but having a more overview to have realistic system performance assessment. And finally, we have other types of architectures which are also considered, for example, architectures based on resonant tunneling diodes, which are known to be very relevant semiconductors for very high frequencies, so maybe even beyond 1 terahertz, or also looking at antenna lenses, which is an alternative to the traditional phased array beamforming approaches. Then the second aspect is to look at intelligent reflective surfaces. So there we use some prototypes that we first model to check how the beamforming can be controlled and validate the control of the different phase components of each individual element, such that we also consider the impact of wideband that we have at higher frequencies and the way this control can be, let's say, broadened in terms of controlling wide enough bandwidth of influence. And finally, those devices, they also need to be integrated into the whole network, obviously. So we need to consider the network challenges. How do we interface? How do we control those RIS devices? And how can we interface the different components such that they perform the necessary reflections when required? Okay, so in short, Deliverable 5.2 is already released. That's everything you have about device classes. And Deliverable 5.3, this will be released by the end of March. And then you will have all the technical enablers, not only the one on hardware and RF, but also the one related to the SOC design or to the ultra-low power devices.
And the WorkPackage 4 also, we had deliverable D4.2 already published, where you can find the extended list of enablers for radio enablers. And in deliverable 4.3, which would be available in May, we are going to have the extended evaluation results for different enablers that would be available. And by this, I would like to thank you all for your attention.